Hello, everyone. My name is Maha Haji, and I'll be presenting the work that I've been doing with collaborators, analyzing the possibility of integrating pumped hydro reverse osmosis systems in the country of Iran. It's a pleasure to be here at the Applied Energy Symposium presenting this work. Iran is the second largest country in the Middle East, with a 2020 population estimated to be nearly 85 million people, which is expected to increase to 98.6 million by 2050. The country is highly urbanized, with over 75% of its population living in cities. Of the 310.8 terawatt hours of electricity generated in 2018, almost 94% of that was provided by natural gas and oil. This heavy reliance on fossil fuels in Iran has resulted in tremendous greenhouse gas emissions, with the country emitting 656.4 million tons of carbon dioxide in 2018. This amounts to 31% of the total emissions in the Middle East and makes Iran the largest emitter of carbon dioxide in the region. Overall, Iran stands as one of the most energy-intensive countries in the world, with a per capita primary energy consumption of over 40 megawatt hours per capita in 2018. Growth in population will lead to a growth in energy needs, and energy generation driven by oil and natural gas will lead to increased emissions of carbon dioxide, which in turn will exacerbate existing environmental and health issues in the country. In addition to Iran's energy needs, water scarcity is a growing issue for the country, where 70% of its area is considered either arid or semi-arid. Overall, Iran ranks as one of the top 4 water-stressed countries in the world. It has an average annual precipitation of 250 millimeters, which is less than 1/3 of the global average. Alarmingly, the aquifer area required to sustain the current groundwater withdrawals and dependent ecosystems is 10 to 20 times larger than the actual area of the Persian aquifer. Significant factors contributing to Iran's water crisis include population growth, mismatch between population distribution and available water resources, promotion of unsustainable agricultural practices, and less than optimal management of water resources. One example of how resources have been dwindling in the country is Lake Urmia, shown in the image on the left, which was reduced to 10% of its maximum in less than 15 years. Rapidly declining water resources and overall consumption growth by increasing living standards are expected to lead to an absolute water scarcity in Iran by 2025. Luckily, Iran has a lot of natural resources that can help combat some of these problems. For instance, Iran has considerable solar energy resources given its location in the world's sun belt. It has an average solar irradiation of 1,800 to 2,200 kilowatt hours per square meter per year, and 280 sunny days on 90% of its land area. The figure on the left shows the potential for solar voltaic energy in Iran. Studies have estimated that Iran has the potential to develop 14.8 terawatts of solar PV capacity. If only 1% of Iran's deserts were covered by solar PV, the generated energy would be 12 times more than the country's annual electricity production. In addition to solar power, Iran's geographic location lends itself well to harnessing wind energy. Low air pressure in most parts of the country, except in the high pressure north and northwestern areas, and the heterogeneous climate combine to produce strong airflows over Iran during the summer and winter months. The figure on the right presents the potential for wind energy in Iran. Estimates of the total energy potential from wind range from 32 to 554 gigawatts, of which the country only has 302 megawatts of installed capacity, suggesting the existence of many growth opportunities. Studies have found a number of potential areas with appropriate power density for wind energy utilization, with at least 18 gigawatts economically obtainable with current technology. In the case of water resources, with a total of 2,700 kilometers of coastline due to the Caspian Sea in the north and the Sea of Oman and Persian Gulf to the south, Iran is a favorable location for the implementation of seawater desalination. In recognizing its acute freshwater supply problem, Iran has embarked on building desalination plants, tunnels, and pipelines to bring fresh water to its parched interiors. And as of 2019, the installed desalination capacity in Iran is estimated to be 1.12 million cubic meters per day, with 58.2% of that achieved through seawater reverse osmosis. In recent years, Iran has ranked as one of the top 20 countries with the largest desalination market. Current desalination plants, however, utilize electricity predominantly generated by the burning of hydrocarbons, which likely exacerbate arid conditions in the country. There is tremendous opportunity to meet Iran's energy and water needs through an integrated approach using renewable energy, pump storage, hydropower, and desalination. Previous research in our group found one can exploit the commonality of ideal head of pump storage hydropower and reverse osmosis plants to develop an integrated approach to increase overall efficiency and reduce capital and operating costs. The figure on the left shows a schematic of such an integrated pumped hydro reverse osmosis system, or IFROS. Excess peak solar and wind power are used to pump seawater up to an impermeably lined reservoir to store energy in the mountains near the sea. When needed, the seawater flows down the mountain and through a primary generator to produce electricity. A small portion of the high-pressure seawater is diverted through an RO plant to produce fresh water. High-pressure brine byproduct flows through a pressure exchanger or secondary turbine to recover additional energy before it is combined with the seawater outflow from the primary generator. As 20 times more water is typically needed for power generation than for desalination, mixing of seawater from the power turbines with brine from the RO system enables direct discharge back into the ocean safely and economically. To investigate the applicability of IFROS in various regions around the world, our previous work developed a Geographic Information System, GIS-based topographic analysis. GIS data was used to determine the locations of regions that had elevations greater than 500 meters, and the elevation of each region was then divided by the minimum distance to the seacoast, resulting in what is referred to here as the I-index. The higher the I-index, the greater the potential suitability for IFROS from an energy storage and logistical perspective. These two factors, the reservoir elevation and the distance to the nearest coast, can increase the value of a project either by providing greater energy storage potential or lower construction costs. Regions which meet a minimum height requirement and are within reasonable tunneling distance from shore are colorized using a heat map of the region so as to allow for rapid assessment of an area for further scrutiny. An overview of the IFROS potential for Iran is shown in the figure on the right. Red regions correspond to areas of high I indices, or areas most suited for IFROS development. There is great potential for Iran along the Caspian Sea and along select portions of the Persian Gulf Coast. In this study, we have identified 4 main regions with high IFROS potential. In the northwest along the Caspian Sea, shown in A, north of the city of Tehran, shown in B, in the northeast near the city of Gorgan, shown in C, and along Iran's southern coast near the cities of Shiraz, Bushehr, and Bandar Abbas, shown in D. In each of these regions, areas outlined by black lines are considered for IFROS development and are detailed in the table on this slide. For each of these areas, it is assumed that only 1% of the land is developed into IFROS. The actual usable amount will require further study that considers environmental, geotechnical, competing land use, and sociopolitical issues that also come into play. Overall, there is the potential to serve the energy and freshwater needs of over 201 million people through IFROS systems, with just 1% of the areas highlighted, more than double the population of Iran projected for 2050. The IFROS potential surrounding the major city of Tabriz is shown in the figure on the left. In addition, it can serve the cities of Ardabil, Zanjan, and Rasht. The best sites for IFROS are located about 220 kilometers away from the city of Tabriz, which, while likely out of freshwater aqueduct distance, could easily be served with renewable energy from the system for all 1.56 million people living in the city. The combined potential for the region, assuming only 1% of the highlighted areas could be used for IFROS, could provide enough electricity and fresh water for nearly 40 million people, which is much more than the population of the nearby provinces of Ardabil, East Azerbaijan, Gilan, and Zanjan combined. The potential for IFROS sites that could serve the city the capital city of Tehran, as well as the major cities of Karaj and Qom, are shown in the figure on the right. It is envisioned that a combination of canals and tunnels could economically deliver immense amounts of fresh water to the parched interior. The IFRO sites could serve Tehran and nearby cities. For just the city of Tehran, which has a population of nearly 8.85 million people, IFROs would require only about 9 square kilometers of combined reservoir area, which is both feasible and practical. The supply of renewably derived fresh water can have particular significance in serving the holy city of Qom, which in recent years has suffered from environmental pollution. Chalus, a popular vacation destination, can power its economy and provide fresh water for its visitors using the abundant natural resources in its immediate surroundings using IFROs. The IFROs potential of the outlined region in the figure could provide overall enough electricity for over 112 million people, much more than enough to serve the nearby provinces. Continuing along the northern coast, we see the figure on the left shows the potential for IFROs to the northwest of the country. Located within 50 kilometers of the major cities of Gorgan and Sari, the development of IFROs in this region could provide enough energy and fresh water to meet the needs of over 26 million people. This region can take advantage also of the immense solar energy potential of the Great Salt Lake, or Dasht-e Khavir, that lies to the south. The potential for IFROs in the south of the country is shown in the figure on the right here. The well-ordered topography of this region is ideally suited for the development of IFROs technology, and the close proximity of major urban and industrial centers provide a strong consumer base. The combination of altitude, 1,600 meters, and distance, approximately 220 kilometers, renders the transport of fresh water from IFROs to the major city of Shiraz unfeasible. However, with a population of approximately 1.5 million people in the city, a system of only 1.72 square kilometers of lake area would be required to meet all the electricity needs of the major city of Shiraz. And the excess renewable power could be used to pump fresh water to the city while enabling development of towns along the course of water and energy transport. The freshwater produced could also irrigate farms, which could provide produce for local consumption and international export. The development of IFROs throughout Iran can also spur job creation in the energy sector. Following job creation factors from Klein et al., we can determine the job creation due to IFROs for both construction and operation stages of the projects. From the regions highlighted in this study, Iran has the potential to utilize IFROs to provide approximately 30.51 terawatt hours of renewable energy generation and storage throughout the country. The jobs created will depend on the particular mix of technologies used, such as hydropower, solar photovoltaic, and wind energy. In determining the total full-time workers needed, we consider that all 30.51 terawatt hours derived from IFROs will be in the form of pump storage hydropower, that the regions in the south of the country will be powered using solar energy, and that the remaining regions in the north of the country can attain 80% of their power through wind and 20% from solar energy. With these assumptions, the total number of jobs created by developing IFROs is estimated to be as much as 33,199 full-time workers in the construction stage and 15,254 full-time workers in the operation stage. As stated previously, this analysis assumes that only 1% of the outlined IFROs regions are developed. While these results are readily scalable, the environmental, geotechnical, competing land use, and socio-political issues must also be considered. There's also tremendous environmental benefits for developing IFROs in Iran. With an average emissions rate of 0.2 kilograms of CO2 per kilowatt hour in 2018, resulting from Iran's heavy reliance on fossil fuels, developing IFRO systems has the potential to offset over 6,100 kilotons of CO2 annually. This has the same effect as taking 2.2 million private vehicles off the road. The availability of widespread renewable energy could also help mitigate environmental and human health costs. In particular, the generation of 30.51 terawatt hours of renewable energy could save on average over $244 million annually in avoided environmental costs and an average of $87 million annually in avoided human health costs. The regions around Iran detailed in this study account for a total of nearly 220 square kilometers of potential IFROS reservoirs, assuming that the depth of each reservoir is approximately 30 meters, and that the total volume of seawater that could be held by these systems is approximately 6.58 billion cubic meters. Then considering a seawater to freshwater conversion efficiency of about 33% for RO desalination plants, and the diversion of only 4.7% of pumped seawater to these RO systems, which is a sufficient amount to ensure proper brine dilution, the total freshwater produced daily from the region, from just 1% of the regions highlighted in this study, could be approximately 102 million cubic meters. This meets the annual needs of nearly 37.3 million people, or over 44% of Iran's projected 2020 population. This slide summarizes the numerous benefits of IFROS development in Iran that we've highlighted in our study. Thank you for your attention, and I look forward to your questions either as part of this virtual conference or via email.